We are Team 21. In this project, we propose KD-S4, which is improved version of S4 that can automatically test lane keeping functionality of self-driving car. Recently, autonomous vehicle has become an important part of the industry. In order to design safe autonomous driving system, the way to find possible accident of autonomous vehicle will be important issue. So, objective of our project is to generate test data for virtual tests of autonomous vehicle. In addition, we target only the lane keeping functionality of self-driving cars. The first part of our project is procedural content generation. By using PCG, we generated the virtual road network automatically. PCG has 3 steps to create random road network. In addition, it has validation method to check generated road map is valid. Let's look at 3 steps of generating road network. First step is road segment. Road segment is the smallest unit of our map. We define 2 types of segment, straight road segment and arc road segment. And road segment is represented by 5 polylines. In this figure, we can see the example of road segment. This figure shows the process of straight road segment generation. Inputs of this process are backline, length, and direction. By using these inputs, we firstly obtain the orthogonal vector of backline, and applying this vector to all points in backline. Then straight road segment is successfully created. Next is arc road segment. Input is backline, radius of curvature, and rotation angle. Through these inputs, we can obtain rotation axis and rotational matrix. Then, applying rotational matrix to all internal points in backline will create new arc road segment. Next step is load and load network generation. In load generation process, we firstly create the short load segment. Then, grow the load by generating random load segment continuously. This process is end if the load reaches any boundary of the map. And load network generation process is simple, just adding new random loads to previous load.
Autonomous vehicles should be able to drive on the generated road network. Therefore, validation process is required after generating road and road network. In order for a single road to be valid, 2 conditions must be satisfied. First, 2 endpoints of the road must cross the map boundary. This condition is always satisfied because the segment is made repeatedly until it reaches the boundary of map. Second, self-intersection should not exist. The figure is 4 cases of self-intersection. Next is road network validation. The first condition of road network is that all roads must have only valid intersections. A valid intersection makes 3 cross points on the left, center, and right lines. Otherwise, the road network is partial overlap. After checking partial overlap, it should be checked that all roads have at least 1 intersection. If a road does not intersect with another road, the vehicle cannot move on that road from another road. Thus, a road without an intersection becomes meaningless in a road network.
Here, using genetic algorithm, we iterate for each generation with size of 25 populations, and the other detailed settings are like this. First crossover method is join crossover, and this is operated like this. Another is merge crossover, and this is operated like this. Finally, mutation is operated like this. And for similarity test, we describe its road network as histogram and calculated difference between them. Within the original research, both join crossover and merge crossover is done with the entity of map. Here, since its fitness is evaluated with path, we thought that its figure lies on its path, not on the map. Within this context, we propose logically improved join and merge crossover operator that done with the entity of path. Here, the crossover point is chosen from path, which is red line from the figure. We can figure out that child is from the parent that including the pet, which is blue and green line from the figure. Likewise, merge crossover is done with the root that including the pet. Existing methods for similarity test cannot notice that there is a big difference between these root networks. Therefore, we also describe the variance of root segments as a histogram. As a result, we can recognize this difference. Then difference of root network is calculated through this process.
To evaluate the road networks, our system goes through the following processes. First, it converts the generated road into good form to simulate. It rotates the road and makes the simulation start point to 0.0. Also, it generates waypoint from the given road. Then, GA program sends generated road and waypoint to Simulink to start simulation. After Simulink finishes the simulation, it sends back the simulation result to GA program. To generate waypoint that simulator would follow, we converted the map into the graph to find out the path with specific priority. To make graph, we defined the intersection of the road as a node, and detailed priorities are like this. To generate waypoint, we find out the path that is sequence of node using the graph. We make path satisfying this condition and select the path that has largest amount of segments. Then, using the paths we made, we finally generate the waypoint. We sequentially connect each node with the centerline of segment that lies between them. For the communication between GA program and Simulink, our system uses two communication protocols. First is TCP/IP protocol used for synchronization between GA program and Simulink, and second is CSV file at designated paths used to share simulation data from GA program to Simulink. Following figure shows the communication flow. Simulink is a graphical simulation program based on MATLAB. In our simulation, we used EgoCar with vision-based lane keeping system. During the simulation, EgoCar drives along the virtual roads following the navigation paths. While EgoCar drives, Simulink observes the driving paths and literal deviation so that it can calculate fitness value. To calculate the fitness value, we used the bounded lateral deviation, which is a distance between the center of the road and the EgoCar. In order to get better evolving efficiency on GA, we bounded the lateral value at larger value than half load width. So, if the fitness value is larger than half load width, we can know that OBE has occurred during the driving.
This graph is our result of simulation. We observed fitness within nearly exponential scale of generation. We can observe that KDH first generally has 1.3 times better fitness compared to the random. The detailed evaluation would be done in the following discussion. This graph is the result of cumulative OBEs. We can observe that KDH first efficiently generate map that having more cumulative OBEs compared to randomly generated map. This graph is the result of occurred vision error. Here, vision error is occurred because vision-based lane keeping system failed, and this can be another matrix to evaluate the map. This graph is the result of time to generate map. To conclude, test data generated by GA is better than one from random. Using map size perspective, large map has higher fitness value and more vision error occurred compared to the small map. Within road number perspective, more OBs occur than multi-road map. Also, map generation time is longer as size and number of roads in map increases. Within this research, our novelty lies on two things. First, our KDH first concept is based on replication of original first system, which generates test data with more OBs and better fitness value compared to random one. Second, we improved the original first as KDH first by proposing improved road generator, search operators, and similarity test method. Most of all, we introduced new simulator as new evaluation method. Our team number is 21, and thank you for listening.